Hello, I'm Tim Lawlor, and thank you for taking the time to listen to my talk on late thermal pulse models and the central star of the Stingray Nebula. The, uh, the late thermal pulse objects briefly are just post-AGB helium shell flashes that occur between the AGB and the planetary nebula phase. What's shown here, the blue track is a late thermal pulse. The earlier are actually AGB final thermal pulses, or what Blocker and Schoberner called AFTPs. Quick history of the Stingray Nebula. The Stingray Nebula has been observed to be dimming between 96 and 2016, shown here in the picture, but before that, for about 50 years, it was heating rapidly. And in the early 90s, it was identified as a very young planetary nebula. Its luminosity, though, has also declined rapidly for 20 to 25 years. And so the most likely scenario is a late thermal pulse object, though some authors have pointed out some problems with this scenario that the models that I have here ought to put to rest. And those are listed here: time scale, rapid ionization, and the rapid dimming, among others, which you can find in the Lawlor monthly notices paper. The time scale problem is solved by late thermal pulse models that I've produced here. Most likely this wasn't a real problem. It's probably just that no one's really dissected the time scales of late thermal pulse models that finely. And so you can see here, this solves both the time scale problem and the rapid dimming and reionization problem, because the timescales here are on the order of 25 years. The sudden appearance of the ionization of the ionized nebula, which usually take millennia, we propose is due to the late thermal pulse consuming hydrogen through proton capture, and this corresponds to the knee here. So the eruption is here, and then the hydrogen is, during this cooling here, the hydrogen is consumed. And that happens very close to the surface. It's a very, very thin hydrogen atmosphere. And so the energy produced is very close to the surface of the star. There is also a problem of the observations being cooler than most models of what seems to be appropriate mass. And that hydrogen ingestion also has the effect of turning the model cooler, here shown in the log G, log T plane. And this is only the case for the models that erupt between 4.6 and between log T 4.6 and 4.7. I'm turning this into a more broad late thermal pulse project, which I hope will be coming out later this year. And so one odd thing about that is that the models seem to always erupt in the same range of temperatures. There's like 3 narrow ranges of temperature where the models always seem to erupt, at least so far. They also seem to erupt at a high percent for models. And so that leads to this question, which was inspired by the organizers' email saying that we should feel encouraged to be bold or controversial. I don't think it's either of those, maybe, but the question is where are all the late thermal pulse objects? Why haven't we observed lots of these if they're so common in the models? And very speculative answers shown here are maybe they're R-core Bohr type stars, similar to FG Sagittae, and you could argue about whether FG Sagittae was a late thermal pulse object or a very late thermal pulse object. Maybe they're hiding in plain sight. Parts of these eruptions last hundreds to 1,000 years, and so maybe some planetary nebula are actually just late thermal pulse objects. And so the question is how many? And I guess that's the part that you might consider controversial. So I'll be happy to be disabused of that by those of you who study planetary nebula more carefully than I have. All right, thank you again. And you can find me, oops, sorry about that. You can find me on ResearchGate or on Penn State Brandywine's website, and you can email me questions. All right, thanks again. And I'll see you around the virtual conference.